Okay, so welcome to lecture 28. Today we're going to go on with the strange story of the strange attractors. And we're going to start from the water wheel equation. I'm just going to make a few comments about it and learn something about it, and then I'm going to tell you how to get it into the Lorentz equation, and I'm going to tell you the whole analysis story following very closely to what Lorentz did. The reason for doing that is the Lorentz equation is non-dimensional, and it's very cleverly put. It's the same equations, but it's very cleverly to minimize the number of parameters. So that's why we're going to do that. But before we do that, let me just remind you what we had with the water wheel equation. We did this expansion of the mass as a Fourier series, or the mass distribution as a Fourier series. And then we derived a whole bunch of ordinary differential equations for the amplitudes of the Fourier series. And then we showed, once we put in the torque balance equation, that the equations decoupled and you were left with only three. So the three were basically for the variables, the coefficient of the sine term in the mass distribution, the coefficient of the cosine term in the mass distribution, and then omega, which was the frequency with which the wheel was rotating as a function of time. And the equations we derived, and we showed that those were separate from all the other higher order ones. And since we only cared about omega, they were the simplest set of equations we had to solve. Okay, so here they are. They are those three differential equations. And remember, as I said, A dot was linear. Was basically, here's the nonlinear term, the omega B1, linear in A1. Here's another nonlinear term, omega A1, linear in B1 and the Q1 is a constant, and omega dot was linear in omega and A1. Okay, all these other things, there are constants. Okay, so it's a reasonably simple set of equations. The nonlinear terms are necessary to have chaos, right? Remember, we proved very, very early on that any linear system in any dimension we could solve using the eigenvalues of the matrix around the fixed point. Okay, so what I'm going to do now is I'm going to go through the analysis just to start, because we've looked at equations like this and then we try to non-dimensionalize them. In other words, we try to rescale the time, to rescale the variables, possibly to change some of the variables so that we wrote down as few constants as possible. So here we have 6 constants, and it actually turns out that the smallest system that you can use for this type of thing is 2 constants. Okay, but sometimes it's not easy to know how to get there, right? We had some cases where we could do it easily. The way that I do it, if I really get stuck and I don't know how to proceed, I actually work out the fixed points, because very often the fixed points identify the new variables for me, and this is what's going to happen here. So I'm going to work out the fixed points and give you a physical interpretation, use that to identify a new set of constants, and then give you the transformation to the Lorentz equations, and then analyze the Lorentz equations. So that's going to be the basic procedure for the day. Okay, so the fixed points, we basically have to set all these things equals to 0, so A dot, B dot, and omega dot. A dot gives us A1 is equals to omega B1 over K. So it's a quadratic equation. There are 2 independent variables over there. B dot equals to 0 gives me another expression for omega A1, okay, which is linear proportional to B1. And omega dot equals to 0 basically gives me an additional expression for A1, right? So there we have omega dot equals to 0. This thing equals to 0, solve for A1, we get that. And so we now, for the fixed points, we have to satisfy all those 3 equations. For the first thing I do is, I said, I've got 2 expressions for A1, okay? Let's eliminate A1 and see if I can say anything else. So let's eliminate A1, and we're going to use the first and the last expression. Okay? Because omega appears in both of them, so if omega is not 0, we can cancel it out. Okay, so we use the first and the last expression, so we can simply put this thing equal to that thing up there and simplify it. And so here we have it. These two are equal. And we can find that that thing is true if either omega is 0, okay, then it is true. It's very important here not to throw away possible answers. Because you're going to throw away possible fixed points. So never do that. Keep all the possibilities. So it's true either omega is equals to 0, or if B1 is equals to this new constant. Okay? And so we've got those two now, and we're going to explore each one independently. So let's say if omega is equals to 0, we simply substitute it back into all these other equations. And what we get is that A1 is equals to 0. Okay. We also get that from this second equation that B1 is equals to K over Q1. Okay. And so we have basically the fixed point, right? Because we have all the unknowns defined in terms of constants. Okay, and what we want to get now is the interpretation of that thing. So what that thing is, it's basically the case where there's no rotation, right? So remember you had your wheel going round, you had the little pipe at the top that poured the water in, and this solution is when omega is 0. So what you simply have is the water's poured in and then it falls out the holes immediately. Okay, at the top of the manifold. This solution might be unstable, but I haven't said anything about that. Okay. And in fact, the one place where it will be unstable is if you're pouring a lot of water in there. If the inflow is high, then it's always going to want to spin. Okay. But it's a fixed point. The second fixed point, in fact, you expect it to spin. So you would almost guess that this thing, at least at some places, was unstable. The second fixed point, this blue possibility over here, is if omega is not equals to 0, then B1 has to be equals to this expression. And then we once again go back and find expressions substituted back into these three equations and then solve for the other ones. So if B1 is equals to that, if we look at A1 dot equals to 0 and B1 dot equals to 0, okay, we get another expression for B1, right? So if we substitute A1 equals to this thing in there, and solve for B1, what we get is that B1 is equals to KQ1 over omega squared plus K squared. So we then have two expressions for B1. We put them equals to each other. We also note that K is a constant that from our physics is greater than 0. Okay, so we can divide by it, put the two B1s equals to 0, and then what we get is simply Q1 omega squared plus K squared is equals to nu over pi GR. Okay, so what we have there is the independent or the dependent variable is omega. We can solve for omega, and we get that omega squared is equals to this combination of constants. Okay, so this is the rotation. Okay, so this fixed point actually has a fixed rotation. It's a solution where the rotation squared is constant. It represents two solutions, right? Because when you take the square root, you have plus minus omega, and you expect that because you expect the water wheel to be either rotate the clockwise or anti-clockwise, which is what the two solutions correspond to. So that's your constant frequency. It's very important, if you get a solution like this, always write down when they exist, right? You can only find the rotational frequency if this thing is bigger than 0. Okay? And it's easier always to write something as bigger than 1. Okay? So I can rewrite this inequality being bigger than 0 as simply pi gr q1 over nu greater than k squared, or if I divide by k squared, it's greater than 1. And what this thing is, I'm going to define a new constant called that, which actually plays an incredibly important role whenever you do fluid dynamics. Okay, that constant is the Rayleigh number. And if you actually look at all the units, you put in the units for the inflow, for K, which is the leakage, for the damping, just the normal physical units, you'll find it's actually dimensionless as well. And so simply by looking at the fixed points, you get a number which is a good guess at a new constant. Okay, so this Rayleigh number appears not here, it appears at many, many places. It simply represents the competition between driving, in other words, how you're putting the fluid in, and damping. Okay, when we look at the convection rolls later on, you'll also get a Rayleigh number, and it'll be related to the temperature, because the temperature basically gives you the competition between driving and damping as well. Okay, so this is the Rayleigh number. So this is going to, we expect this to be a new constant in the dimensionless parameters. We also expect something like this to be a new constant in the dimensionless parameters, once again because it appeared in the fixed points. Okay, one thing you can see here is this thing fails to be bigger than 1 if there is too much damping. Okay, so you can't have steady rotation if you've turned the brake on too hard, which you kind of expect. So you always check whether the intuition is right. And so now what I'm going to do, that's all I'm going to do with the water wheel equations. You basically, the fixed points are two solutions. One rotates left, the other one rotates right. The third solution is no rotation, but we suspect it's unstable. And what I'm going to do now is I'm actually going to give you the transformation to the Lorentz system, the answer. There's a way of deriving it in one of the exercises in Strogatz that will be worthwhile looking at. But I'll simply give you the answer at the moment. So the thing is, once again, like we have done in all the previous times we non-dimensionalized the problem, we rescale time and we rescale it with KT. You have a new variable, x, which is simply omega over k. You have a second variable, y, which is basically related or proportional to A1 times a whole bunch of constants. And a third variable, z, that's proportional to B1 times two constants plus a constant over here multiplied by CR, which is that new Rayleigh number. Okay, and if you do that and you define new constants, which is basically, these are the constants that appear in Lorentz's equation, is basically B equals to 1, sigma is equals to this combination of constants, and R is your Rayleigh number. If you define these new constants, you can actually get directly from our water wheel equations to the Lorentz system, which I'll show you on the next slide. So that's just, it's not a complicated relationship. It's all simply rescaled variables, and here I've added a constant to the variable in Z, and then you have the Lorentz system. So they're very, very close. Okay, so that's where I'm going to leave the water wheel equation. I'm now going to go and look at the Lorentz system. The only thing to notice, and this is why I said the water wheel equations are less general than the Lorentz system, because we've set one of the Lorentz constants equals to 1. Okay, so it's a special case of the Lorentz system. And this is also why I said when you see that the Lorentz system arises, there are only 2 parameters effectively in the water wheel equation, not 6, as I put up here, that determine the dynamics. Okay, so now I'm going to say a few things about the Lorentz system and then give it to you, and then I'm going to start analyzing it, and I'm going to start boxing in the possibilities that we had. Your question yesterday actually made me think. It was a good one. The one comment is, in a one-dimensional system, what are the possible attractors? Yeah, stable fixed points. You can go to fixed points. and the thing to notice there, you have one dimension, the attractor is 0-dimensional, the biggest attractor. If you have 2 dimensions, what are the attractors? Yeah, what's the dimensionality of a limit cycle? Yeah. No. 1. It's a line. So your largest attractor is 2 minus 1. In 3 dimensions, you would expect there at least to be an attractor of dimension 2, right, if you follow the pattern. But it turns out there's more than that, because there's attractors between. You can eliminate an attractor of dimension 2 is basically a plane. You can eliminate that one. Well, you can keep that one, but you have other things in between one-dimensional lines and planes, and this is what we're actually going to see arising. And seeing the argument for that is actually quite useful. Okay, so the Lorentz equations, just a little bit of background before we go into the mathematics. The paper, in fact, the derivation is this one. It's a very famous paper. It's worthwhile looking at. You'll actually see that a lot of the analysis that Strogas does is actually to be found in that original paper. I'll see if I actually can find it and put it on the website. But sorry? If you got it. Okay, so it's easy to get. Yeah. Okay. So that's his paper, and a lot of the stuff that we're going to discuss basically comes directly from there, possibly with a little bit more modern notation. Did you actually look at the pictures? Yeah. 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 Well, don't rush. We'll do it all of next week. But a lot of the stuff we're going to use comes from there. And you'll see actually in that paper, the things are hand-drawn. A lot of, because they didn't yet, which basically shows that he really had good insight. He simply looked at the numbers and played and was committed enough to actually try and find it out. Okay, so he derived the derivation of the equations is also there. It basically comes from 2 convection cells. He wanted to know if you have 2 of these rolls, what are the particles going to look like? He was trying to understand weather systems, tornadoes, how these things start, and how air moves between the 2 of them. And it is the first example of a chaotic attractor, the very first one that was actually understood, which makes it amazing as well as his analysis. So the one thing I should say, before him, chaos was anticipated by Henry Poincaré, right? And it was even discovered there's a different type of chaos, and I'll explain the difference as we go along, that occurs in Hamiltonian systems that necessarily have to be written as 4 equations. Okay, so a 4-dimensional system that comes from a Hamiltonian system does display chaos, and Henry Poincaré described how it would happen. Okay, but that's one step more complicated than this system because we're still in 3 dimensions. Okay, he also showed that chaos exists, but they don't have attractors in these systems, and the argument for that is. I can answer afterwards, but I'll just leave it for now. I'm just going to say it. So Hamiltonian systems are, chaos was there, it was anticipated, but they didn't expect an attractor. So what made Lorentz's thing unique is the fact that you can have the strange attractor. Okay. Lorentz's analysis methods were also revolutionary. The way he looked at it was just totally different from any way anybody had had analyzed the dynamical systems before. Up until this point, people were basically taking the equations, doing perturbation theory, like those expansions that we did. They became very, very good at that, and it can become really, really nasty. And if you had done the course before I got here, you would have done a lot more of those expansions. Okay, so that's basically what I replaced to put the Lorentz equations into this course. Okay, it's not to be sniffed at, but it's become less relevant now that we have computers that can integrate things as fast. There are places where those expansions are still useful. I used a lot of them, and I'm actually quite good at it when we looked at Einstein's equations, because there's certain places where you can't numerically integrate the equations, but you can do the expansion. So it's very useful. So don't think it's like gone, but it's just I wanted to give you a broader base. Okay, so his methods were revolutionary, and he introduced a lot of new things into dynamical systems, a lot of new things of how to look at it, and we'll look at some of them now. Okay, so let me just give you the Lorentz equations. So remember there were 3 parameters and 3 unknowns. Okay, so, and remember for the water wheel equation we had x dot or omega, which is related to x dot. It was just linear, right? It was the parameter times the linear y minus x thing, and the same thing is true of the water wheel equation. So you had one equation that is linear. Y dot is equals to r, which is that Rayleigh number, x minus y, so this part is linear, and then you added this minus xy term. Okay, so that's quadratic. The second one is z dot, which is equals to minus b, which is your other parameter, plus another quadratic term. Okay, and the reason why I like analyzing this set of equations is, remember I said whenever you non-dimensionalize, you want to make your complicated parts as simple as possible, the coefficients. And what Lorentz has done is he's written it in a form where your quadratic terms simply have 1s in front of them, okay, which is useful when we analyze the thing further. So this set of equations is, in some sense, one of the simplest ways of writing the Lorentz equation. You can change variables and put it in other disguises, but this is the classical one, and it's reasonably easy to analyze. Okay, so the 3 parameters we have for the water equations, b is only equals to 1. They're all positive, and I'm just going to name them if you ever come across them. If you do fluid dynamics, this is the Prandtl number. This is that Rayleigh number, that's the competition between driving and viscosity. And b is the aspect ratio, right? Okay, so those are the 3 constants. Let the physicists worry about that for a little bit from now on. But what we're going to do is look at what we can learn from the equations. Okay? An important thing is, somehow once people understood this attractor, they actually derived the same equations in a number of other models. And because they then knew the properties, which were understood for the first time, they could say more things about these models than they had previously. Previously had these models that behaved really oddly. Nobody understood them until Lorentz did the analysis. Okay, so you get them in lasers. You get chaotic lasing, which is sometimes quite dangerous. You get them in dynamos. Like the dynamo at the center of the Earth, does these people say it's switched polarity? And this is one model for it arises there. Oh, sorry, the Lorentz equations also arise naturally when you start looking at dynamos. Okay, and you get it in the water wheel. And so what we're going to do now is list systematically all the properties of the Lorentz equations and start making the case for the strange attractor, and more importantly, limiting the parameters where we can find different behaviors. Because when you get the set of equations, and remember when you saw that video from Strogatz, there's places where it's going to look like an ordinary pendulum. It's just going to go round. It's going to have almost constant rotation. There's places where it's going to stand still. And then you have this very reasonably small region where it does this really weird stuff. And so we're going to basically start boxing in where the different phenomena occur. The first thing is the equations are symmetric if you let x and y go to minus x and minus y. So there's a symmetry when we look at the solutions. Okay, so just look up here. If you replace x with minus x and y with minus y and multiply this whole thing with a minus, it remains the same. The same thing here, x with x and y with x with minus x and y with minus y, and multiply through by a minus, and then z just remains unchanged because the minus is cancelled there. So the equations are symmetric, and therefore you're going to see that when you saw those 2 butterfly wings that are integrated, there's a symmetry there. They left and right look the same. Okay, so the trajectories come in symmetric pairs. And so if x, y, and z is a solution, so is this one. Okay? Seems easy, but it sometimes simplifies things. The next thing that we're going to have a look at is the system is dissipative. Okay, and this is what makes the system different from a Hamiltonian system. And it's also useful to define what dissipative means for a differential equation. So dissipative is a concept that you know from physics, right? But in mathematics, it actually has a very, very real idea. And what it means is, suppose you start in your phase space, like view your phase space as a flat thing, and suppose you start with a ball of initial points in the phase space, and then you evolve those points, right? They're all going to move. So if you were to evolve them uniformly, you could like move the whole ball to the right for a certain set of differential equations. But most commonly, you have a set of functions, so this ball is going to deform. And the definition of a dissipative system is, if you start with the original ball of initial conditions, you evolve it, say, for delta t. If the volume that's enclosed by these initial conditions shrinks, then we say the system is dissipative. Okay. And you can see where that goes, because if you think in lower dimensional stuff, suppose you had 2 dimensions and you were around a fixed point, right, an attractive fixed point, right? Okay, this is where the connection coming. You could have a ball of initial conditions around it. You would evolve them and they would all shrink. Okay, so the dissipative system generally tends to mean that your fixed points or your attractors are a lower dimension than the actual dimension in which you're working. Okay, so there's a connection between dissipation and what happens in your phase space. Another example, remember we showed when we worked with conservative systems, you couldn't have attracting fixed points. We proved that was impossible. Another proof is that in conservative systems, there's no dissipation. Okay, so in 2 dimensions, whatever you do, the thing, you may deform the circle, but you can't change the volume of it, the equations. Okay, so these things become connected at a deep level. So let's do this. Okay, the system is dissipative. The volume in phase space contracts under flow. That's basically the mathematical definition of dissipative. And so what we're going to do now is show this explicitly, and we're going to show how the volume evolves, okay, under flow, given a set of differential equations. So you can test any differential or set of ODEs you get, you can test whether or not it's dissipative, and we're going to derive the test now. And so how the test works is, or how the derivation works is, pick any initial volume, like the set of points we initially have. Okay, and in that volume, you're going to have your coordinates x, y, and z, and you're going to have a volume element which I'm going to call dv. Okay, and now what we're going to do is look at those fixed points, sort of let them drift according to the differential equations, and look what the volume does after a while. Okay, so sorry, this is just another thing. This is the surface element of the volume, and we want to see how this thing moves. So after, and the surface element always has this outward normal, which I'm going to need to actually do the math. Okay, so that's our volume element. And what's going to happen now is we're going to let every single point in that volume flow according to this differential equation, right? So suppose I was there and I could work out what x dot is just by evaluating f, and I would know that this point, say, would flow in that direction. Okay? And say a point up there would flow in this other direction, and a point up here might flow in a completely different direction. And after a certain amount of time, I'm going to collect the surface again, and I'm going to draw the new volume. Okay? And I want to know what that new volume is. Okay, so there we have it. We have our blue volume, and we evolve every single point in the blue volume, and after delta t, we find the collection of those points, and we want to know what the new volume is, and we preferably want to work it out from the differential equation without actually integrating the equations. And we can do that infinitesimally. So the way we do it infinitesimally is to notice that when you're here, only the outward part of the flow that took place normal to the surface area is going to contribute to the change in volume. Right? This part that lies within the surface is not going to change the volume. So how this works is this perpendicular component is simply x dot projected onto n, and We know what x dot is, so we don't even have to evaluate it. We don't have to integrate it. We know it's f of x. So we can simply evaluate the velocity vector at each point and project it onto the normal part of the surface. Okay, so let's just blow these things up. Here you have your surface element. This point is going to want to flow in that direction, but only the actual blowing up of the volume surface is going to increase the volume. So only the component that goes of the x dot that is parallel to n is going to make a contribution. Okay, so this little surface area is basically going to move in that direction, and the new volume is simply going to be the surface area plus or multiplied with this displacement in the normal direction of the way that the trajectories have moved. Okay, so that's what we're actually going to use at each point to work out the change in volume. Okay, so the volume contributed by this patch ds is simply little change in volume is the velocity perpendicular to the normal of s multiplied by dt. And so the volume at times t plus delta t is the initial volume plus all these contributions of the little changes in volume where your surface area has moved. And if we take the limit as big delta t goes to a differential, we simply can say replace the sum with an integral, and we have that it's dt times this integral times the perpendicular velocity times ds. And so we can basically see that this thing, the red minus the blue over dt, is simply the differential of v, and that's equals to this integral. Okay, and we can go do even more, make it even easier to calculate, because we know that this perpendicular velocity is just x dot times n, x dot dotted in with the normal vector. We know what x dot is. It's f of x dotted in with a normal vector. And we have another thing called the divergence theorem, because defining the normal vector is sometimes tricky, so you want to avoid that. So we can write this, use the divergence theorem to write this surface integral as a volume integral. It's also known as Green's theorem. That just looks like this. So we now take the integral over the full volume of the divergence of f dot dv. Okay, and that's going to tell us how the volume is changing, which kind of makes sense, right? The volume changes. This f is the flow. How the flow diverges out of the volume is going to change the volume. So if you have flow flowing inward to a fixed point, your volume is going to shrink. Right, so that is how we calculate whether or not it's a dissipative system. If for every volume dv dt is negative, then it's a dissipative system. That's the definition of our dissipative system. Okay, so that's definition. Let's now apply it to Lorentz's equations. Okay, so the phase volume evolution, that's just what the result that we got, is simply dv dt is simply the integral of the volume of the divergence of the flow field. And let's work out what it is for the Lorentz equations. Okay, so for the Lorentz equations, the divergence of f is simply ddx times the first component plus ddy times the second component plus gdz times the final component. We write all those things down, so it's minus sigma minus 1 minus b. And remember, we know all these things to be positive by definition of our physics. And so we know we're going to let this whole thing equals to a new constant, which we're going to call CL, and we know it's less than 1. Okay, so for the Lorentz equations, regardless of which volume you have, it always shrinks. And it always shrinks very, very quickly. Okay, so you can basically write this out. V dot is simply the integral over the volume times the divergence of f dv. So it's simply minus CL times the volume itself. And look, I haven't specified which volume it is, so it's true for every single volume, regardless of where you start. Okay, and so the volume shrinks very, very quickly with an exponent bigger than 1, minus 1, sorry, smaller than minus 1, from whatever it starts with to 0. Okay, it shrinks exponentially fast, and so we know all the attractors definitely have a volume of 0, which is to be expected, right? All our other attractors always had a dimensionally lower than the dimensionally of the initial differential equations. And in particular for the Lorentz system, we basically have that all the trajectories eventually enter some limiting set, right? In fact, so what this thing does, it eliminates the possibility for them to blow away to infinity. They're all eventually going to get stuck somewhere. We just don't know what the limiting set is. Okay, but we do know already of it that it's got 0 volume. In other words, its dimensionality is less than 3. And so it can be a fixed point, that's fine. It can be a limit cycle, which has dimensionality 1, or it can be something new. And so what we're going to do subsequently is start eliminating the fixed points and the limit cycles and look for the parameter space where we get the something new. Okay, so just another thing, I just want to draw the picture for you. So an example of the strange attractor, which is what we're going to derive, is this thing that I showed you the video of yesterday. Okay, so this is a strange attractor. It's got dimensionality less than 3, or less, basically just more than 2. And that is a limiting set. But before we get there, let's start eliminating the other possibilities. So firstly, let's compute where all our fixed points are. And this is very similar to what we did for the water wheel equation, but I need it when I'm going to go on. So the fixed point when they're all equals to 0 basically means that y star is equals to x star from the first equation. From the second equation, we have that y star is equals to x star times r minus z star, and z star is equals to x star y star over b. Okay, which we have, if we substitute y star equals to x star back in here, is equals to x squared over b. And so if we look at this, the first equation, this combination, which is very similar to what we did with the water wheel, implies that this thing must be satisfied. And so once again, we simply have the two cases. Okay, either x star is equals to 0 or z star is equals to r minus 1. Okay, remember the x star equals to 0 was the 0 rotation case. And so let's do the first one. If x star is equals to 0, then the other two are also equals to 0, much exactly similar to the water wheel. And so the fixed point 0, 0, 0 exists for all the parameters. If z star is equals to r minus 1, what we have is x star equals to y star. We simply solve this equation. So x star is equals to b times z, plus minus the square root of that. And x star is equals to y star. We have x star is equals to y star is equals to plus minus the square root of b times r minus 1. So those second two fixed points exist if r is greater than 1. Okay, so there's a bifurcation that takes place at r equals to 1 for those two fixed points. And so you go on, and I'm just going to finish the stability for today before I go on next time with looking at what the fixed points mean. So let's work out the stability. The nice thing about the Lorentz attractor is the Jacobian is reasonably simple, right? You just take the derivative with respect to x, it's minus sigma. The derivative with respect to y of the first equation is sigma. Then you have the derivative with respect to x of the second equation, which is just r minus z, the derivative with y is minus 1, the derivative with respect to x, with respect to z is just minus x, and then you have the thing at the bottom. So it's a almost full matrix, but it's something you can actually compute, which is not always true of all. It's a simple, let's just say it's a simple matrix. It does depend on the dependent variables in terms of x, y, and in fact z as well. Okay, so let's just examine it for the fixed point at the origin. I'm going, and you can simply say put 0, 0, 0. Then you have this three-dimensional matrix that you now have to solve. It's a constant coefficient system, and you have to work out the eigenvalues of it. Okay, and so you write down, this is just a little bit of a reminder of what happened earlier on. You write down the characteristic equation. In other words, you minus lambda on the diagonal, and then you work out the whole determinant. And in this case, it actually splits up because you have zeros and zeros there, and only in that case, you can have minus lambda minus b, so this bottom thing, multiplying the determinant of the top thing. Okay? Be careful if you have components in here, like we will have with the next two fixed points. You can't do this. It doesn't decompose. You actually have to work out that full determinant, and it is quite an explosive formula, right? You have to use that, you have to work out the full determinant of the 3x3 matrix. Okay, so the nice thing of this thing is that it's factored out. So we can already look at this one. We know that the one eigenvalue is equals to minus b, and we know that since b is positive, this is less than 0. So this is in some sense your shrinking direction. So near the fixed point at the origin, we're going to have that z dot is equals to minus bz. And so z is basically going to approach 0 exponentially fast. Okay, so the motion around the origin is going to be restricted to the xy plane. If we then look at the second part, we can work out the trace and determinant because it's basically a 2x2 matrix. And we find that the trace is less than 0 since sigma is positive, and the determinant is sigma times 1 minus r. Okay, so that is positive if r is less than 1 and negative if r is greater than 1. So if r is greater than 1, you're going to have a saddle. And if r is less than 1, you're going to have either a stable spiral or a node. Okay. So this transition, so r, the fixed point at the origin becomes a saddle when r is greater than 1. So it's only stable over here. So if we start looking for strange attractors, we're going to start looking for r greater than 1. Okay, because we've eliminated the possibility of a stable fixed point. Okay, and I think, I'm going to stop there. I'll have a look at the other two fixed points tomorrow, because they actually play, the other two fixed points sit in the middle of the strange attractor, right? So what the sort of the preview is, you work out the other two fixed points, you can work out whether they're stable, where they're stable, and the moment they go unstable and r is greater than 1, there is absolutely no fixed point, stable fixed point in the whole system. So the possibility then is you either have a limit cycle or you have something new. And you basically, what Lorentz did is he ruled out the possibility of a limit cycle and proved you had something new, and then went on and analyzed it. Okay, so we're going to go on with a mystery story. We're just basically laying the foundations today. Tomorrow next time we'll look at the fixed points again, and then start making the case for the way that Lorentz analyzed the strange attractor. The SIC test, if anybody is interested in writing it,